Hello, happy Thursday and Friday, I guess. Today will be a relatively short day for notes. So you need to make sure that you look at the key for the converting the moles to atoms to mass and the average atomic mass assignment from last class. So that is on the agenda. So you guys can click on that and double check your work. And please ask me if you need any help with that. So today we're going to talk about the arrangement of electrons in atoms and kind of what we can do with that in science. So we've been talking obviously about atomic structure, how to know if something is an ion or an isotope, if it has a charge or not. And we're going to be applying that today in looking at the way atoms give off light energy and what that has to do with electrons. So just to begin with our basic properties of light, I am sure that you have seen an electromagnetic spectrum at some point, and this is a nice example of one. So when we look at electromagnetic radiation, it's really just a form of energy that is moving and it has wave-like behavior. So all of the electromagnetic radiation, the different types of that, make up our electromagnetic spectrum. So when you see this picture here on the right, you know it starts at radio waves. You can see the little squiggly line underneath of that is representing that radio waves are very large, so they're very long waves. They can honestly be up to like several city blocks in length. They're very large to make one full cycle. And then you move your way across to the right, and those waves get smaller and more frequent. So you do need to know that relationship that if you have a large wave, a long wave, like a radio wave, the wavelength is very long, which means the frequency is very low. And then on the other end of that, where you have X ray and gamma ray, the frequency becomes more frequent, and in turn, the wavelength is smaller. So if you see on the bottom of this picture, you have visible light spectrum, right? So there's just a small portion of electromagnetic waves that we can actually see as humans. And on either end of that spectrum, where you get into the infrared and ultraviolet, there's some different animals that can pick up those waves with their naked eye, but most humans can just see the visible light spectrum. There's been some research stating that some people can actually see ultraviolet light, people that have different like genetic malformations of the rods and cones in their eyes, but it's pretty rare. So, with the properties of light, you do need to know that any kind of light is going to move at a constant speed, and the speed of light is 3.0 times 10 to the 8th meters per second. So, any type of electromagnetic radiation will be dependent upon the wavelength and the frequency of light. So it's just some more examples here at the bottom left. It goes over again. The high frequency gives you a short wavelength, and a low frequency gives you a long wavelength, which makes sense, right? Because you cannot fit the same amount of waves into the same space if they are as long or longer. So, with your types of electromagnetic radiation, just some more examples on the bottom of what those could be used for. And you get different types of electromagnetic radiation depending on how much energy they have. So, these long, large waves would be lower energy, and these tight, frequent waves are higher energy. For some definitions, your wavelength will be the length of one full wave cycle, and that can be measured in many ways. So, let's see. Oh, I don't have a pen today. That's great. So, with the wavelength, like we looked at here, you can see, like if we're looking at this one, it goes up and then down and then up. One full wavelength is one cycle of that wave. So it could be from here where we start all the way up and back down. That could be one wavelength. One wavelength could also start at the median and go all the way down and up. That could be one wavelength. You're just measuring one full rotation, so one full cycle up and down. Frequency will be the number of waves that pass in one given time frame. So usually we're talking about the time frame is a second, 1 second, and that is measured in hertz, which we will talk about soon. So wavelength and frequency are inversely proportional, and if you remember from the beginning of the year, we did discuss this briefly, that inversely proportional just means that if one part of that, one variable will increase, the other will decrease, and that's true with frequency and wavelength. They're also mathematically related. So if you look at the equation on the right hand of the screen, you have c, which is the speed of light. So a lowercase c is the variable you want to use for that, equals lambda v. So lambda is a Greek letter and it represents wavelength in meters. So when you write that, it kind of looks like an upside down Y. And if you are trying to type it, you can insert a symbol. But if you just want to write it out, you can just write it as an upside down Y. And then that will be lambda times v, which is going to be the frequency of the waves in hertz. So v usually represents velocity, which makes sense here because one wave will be a distance, right? And that's divided by time. So distance divided by time is velocity. So that's where that comes from. So what we have here is that the speed of light is equal to wavelength times the frequency of the wave. This brings us to the photoelectric effect, which is the focus of the lesson today and what you'll be doing your work on afterward. So the photoelectric effect is the emission of electrons from metal when light shines on metal. So this is discovered by obviously shining light onto metal, but the light is a form of energy capable of knocking off electrons. So we know that light acts as a wave, or it can act as a wave. And so when you shine light, it's energizing these electrons within the metal, and it is actually causing some of these electrons to be energized so much that they leave. They have so much energy, they're going to be flying around. They're going to leave the metal. So light can be that energy that is capable of knocking these electrons off, but it needs to be just a certain amount of energy in order to work. The photoelectric effect was discovered by Max Planck in 1900. He's actually quite famous. He has research centers named after him. So he suggested that heated objects emit small, specific amounts of energy. So any energy. So if I had like a pot on a stove, that heated object would emit small amounts of energy. So that small, specific amount of energy is called a quantum. A quantum is just like a unit, basically, that we're going to be using. It's a term that can be used to describe how much energy is lost or gained. So a quantum is the minimum amount of energy that can be lost or gained by an atom. Planck also used this information and created his own constant that would fit into this formula. So this shows the relationship between a quantum of energy and frequency of radiation. So the minimum amount of energy needed to energize something related to the radiation that it will produce. So this formula is E, and E is representing energy in joules. H is Planck's constant, so it's a constant, it will never change, it will always be 6.626 times 10 to the negative 34th. And then V again is your frequency of radiation. So there's a relation to speed of light and wavelength with this, which you see on the right hand of the screen. So not only is energy equal to Planck's constant times the frequency, but energy is also equal to Planck's constant times the speed of light divided by the wavelength. Shortly after Max Planck came up with his constant and relationship, in 1905, Albert Einstein then expanded on this idea and came up with the theory that electromagnetic radiation has a dual wave particle nature. So hopefully you've heard that before. So that light is going to behave both as a wave and a particle. And so he called particles of light photons. He also stated that the energy of a photon depends on the frequency of its radiation. So if you look at this formula, it is very similar to Planck's formula. So again, we still have energy is equal to Planck's constant times the frequency. We just added the subscript here showing that the energy is specifically talking about a photon. So this means that photons must strike electrons to knock them loose. And then it's also transferring its energy from the photon to the electron, which causes the electron to leave. So if you look at the picture on the left, you have the photon of light being shined onto the atom, or the light is being shined, and a photon of light comes down and it collides with an electron. So this causes the electron to become more energized, and so it jumps out to the next energy level. So when you start moving your electrons around, this is when your atoms can produce light themselves. So you have two states that you want to be aware of, that you have the ground state will be the lowest state of energy for an atom. So the ground state would be just the neutral state, so an unenergized atom. Wherever its electrons normally would fall, that's where they would be. An excited state is an atom has more energy than normal. So an excited state would be, an example would be if you shine light on this atom at just the right amount of energy, you've energized that electron and now it has jumped out an energy level. You are going to get nice colors or light being emitted from these electrons or from these atoms. So whenever the electron goes back to its ground state, it's going to release a photon of light. So we're energizing it. This electron is moving to the excited state. Eventually, it uses up that energy, gives off that energy, and the electron goes back down to the ground state. So when that happens, that excited state back down to the ground state, that atom is going to give off a little bit of light. So that's where the line emission spectrum is used, or how it's created. So a line emission spectrum is specific to each type of atom. So like here's some examples. Bromine, this first one, bromine's very beautiful. So you can see these very distinct bars of light in different areas. And when you energize these atoms and they start going back down to their ground state, um, it's a cycle. They'll keep going back and forth until the energy is gone. And when that's happening, they're going to give off specific bands of light that have to do with their atomic structure. So, with the line mission spectrum, each one will be specific to each type of atom. And then you can shine a narrow beam of light through a gas, and it's going to show these bands of light. And these are kind of akin to an atom's unique fingerprint. Each atom will have its own, and this is where neon lights come from. So, the discovery of the line emission spectrum led to quantum theory, which is what we've been talking about. So, when an excited atom falls back down to its ground state, it's going to lose energy in the form of a photon. So, we know that energy is not created or destroyed. So, this energy came from somewhere, and in this case, it was a photon of light. It could be energy from heat or even electricity. There's other ways you can add energy. So this energy comes in, it excites the electron, and then it eventually loses its energy again. And so when this electron falls back to the ground state, it's going to release a photon of light. So that's where all these beautiful colors come from. And that's the end of this section. So please check Canvas for your assignment and let me know if you have any questions. It will be a gizmo. These do work better on computers, apparently. They do work okay on the iPads, but sometimes it's more difficult to manipulate things. So please check there for the assignment and if there's anything else listed. So please let me know if you guys need anything, and I hope you have a great day.